I'm Mike Georgelis, North American Sales Manager for TMC. Today, I'm going to talk about the different types of vibration cancellation systems available to original equipment manufacturers for ultra-precision instruments such as electron microscopes, NMRs, interferometers, and other types of ultra-precision equipment. Let's start with a typical 4-post isolation frame. This type of frame would be very commonly found in a number of high sensitivity instruments, oftentimes supporting things like a process chamber, an inspection stage, or vacuum chamber, in instruments like electron microscopes, CD SEMs, wafer temp prep tools, even gene sequencers. The isolator used in such a frame is a typical pneumatic isolator insert consisting of a sealed air chamber, a diaphragm, and a gimbal type isolation piston. A sealed air chamber type isolator like this is essentially a mass spring damper system, which can be represented by a free body diagram including a mass, a spring with constant K, and some sort of damping mechanism with damping coefficient C. In a sealed air chamber type design, your spring constant K is proportional to the air pressure inside the sealed air chamber, where higher air pressure is a higher spring constant, therefore a stiffer isolator. And your damping coefficient C is typically provided by friction of mechanical components, such as resistance within the rubber diaphragm itself, which provides the air seal, but also can be increased by adding some sort of viscous fluid to provide additional damping. Pneumatic isolators like this are available off the shelf from TMC, and they can be easily incorporated into any square cross-section frame design. Pneumatic isolators can also be replaced by die springs, which don't use air and are simply a mechanical spring. This type of isolation system provides excellent high frequency vibration cancellation, but often has a resonance in low frequencies. When looking at a logarithmic chart with a very soft spring would have a low frequency resonance around 1 Hz. So you'd see a resonance and isolation at higher frequencies. If you need to get more vibration cancellation and your system cannot tolerate a high degree of resonance, an active cancellation system might be required. When deciding on the type of active cancellation system that's needed, we need to consider 2 use cases. In the first use case, requiring an active cancellation system, you have the same mass spring damping system that we described previously, and a vibration disturbance force that's generated by the instrument itself. So whatever is on the payload is vibrating. In the next use case, again, we have our same isolation frame, but the vibration input is coming from the floor, which can be environmental disturbances from things such as nearby traffic, nearby rails, vibration in the building due to other machinery, and human motion. Of course, the 2 use cases can be combined, and you have a combination of floor noise as well as instrument generated noise. Each use case requires its own type of mitigation. A common way to isolate instrument-generated noise is by using a parallel type active cancellation system, which is capable of using both feed-forward and feedback sensing to cancel out stage motion and machine-generated noise. A common configuration of such a system would be found in TMC's ElectroDamp product line, where you have an isolated payload supported by a sealed air chamber pneumatic isolation system. And in parallel to the passive isolator, there's a Lorentz-Fortz motor, also known as a linear motor or voice coil motor, that acts in parallel on the payload. These can be oriented orthogonally to exert forces in the left-right direction, as well as in and out of the page. A feed-forward loop is often employed, as well as a feedback loop. The feedback loop uses a sensor on the payload to send a signal to a controller, which then has the motor counteract the signal sent by the sensor. Feed-forward control is also used, as the controller can send another signal to the motors, and because in a tool where the motion that is inducing the vibration is often known, we can begin to use the motors to counteract any vibration before it even occurs, resulting in extremely fast settling times. Floor vibration cancellation requires a different type of technology, which we call a serial type active cancellation system. The second use case of a mastering damper system supported by an active cancellation system would have a free body diagram that adds some additional components. Let's start from the top. Here is your isolated payload. Here is the mass spring damper system that we've been describing supporting the payload. Now, replacing the floor is an active piezoelectric serial type cancellation system, which consists of a stiff passive isolator on a low mass stage called an inner mass, and then a load-bearing piezoelectric actuator. The feedback control system in this configuration utilizes a sensor placed on the inner mass. That sensor sends its signal to a controller, which then sends a signal to the piezos to expand and contract in the corrective displacement, keeping the sensor signal at zero, which is what an active cancellation system is meant to do. Here, we have a system that is ideally suited for floor vibration, since the sensing feedback loop is completely isolated by any payload noise and frees up a good deal of control bandwidth to focus on low frequency cancellation and expand and contract the piezos to provide the proper displacement. This spring, at the second stage of the serial type system, provides that isolation. So if there is a good deal of payload motion, it's independent of the sensing feedback control system. Another advantage is The primary system can then be upgraded into its own motion cancellation system. So a linear motor and feedback and feed forward type technology can be added in parallel here to create a system that not only has excellent settling time and high frequency cancellation due to the soft spring, but also excellent low frequency cancellation and an independently operating floor vibration cancellation system. Parallel type systems, such as our electro-damp motion cancellation system, are best used for step and settle type applications for OEMs who need rapid settling times. It's also ideal for position control of tool components. The types of instruments that we would see settling time and position control sensitive are things like wafer inspection tools, wafer temp prep tools, gene sequencers, as well as a number of photolithography type applications. When floor vibration, not settling time, is more of a concern, you would use a serial type piezoelectric cancellation system like our stasis to support the entire instrument. Again, that instrument can be any of the former instruments I mentioned before, and you can even build the piezoelectric systems into the system, such as using one of TMC's stage base or tool base type products, which can be used integrated with a typical 4-post frame in a configuration that might look something like this. Where your first stage of isolation is a pneumatic mass spring damping system, which may or may not have an additional electro-damp parallel type active cancellation system, supported by your second stage of isolation, which are the serial type piezo isolators I had mentioned before. Thank you for joining me today in discussing vibration cancellation systems for OEM equipment. If you have any questions, please contact us at tmc.sales@amatech.com.